I discussed about this large signal analysis for both common mode input as well as for differential inputs. So now what we do is that let us try for small signal analysis for differential input. Okay, I want to make a differential gain out of the circuit. Now the way that I am going to evaluate the differential gain, the computation of GM times R out. Okay, shall we try to do that? Yeah. So now what I do is that I just try to evaluate the capital GM first, and then later we'll try to evaluate the R out. Now what is the condition that I need to place when I try to calculate the value of GM for the circuit? Okay, so the very first condition is that the output has to be shorted, and look for the current I out whenever I have this VID, right, or V in to the structure. So the similar structure has been replicated here, and this is what I have. I have my VID, and right now the question is that is the circuit is symmetric, so that we can apply all those results that we have got. Okay, so now the symmetry of the circuit is being observed right from the input, because a GM is something that relates my input to the output, right? So the capital GM is nothing but I out by VID. Okay, now from the perspective of this VID, I am just looking whether this particular circuit is symmetric under its input condition. Now you have to tell me whether the circuit is symmetric under that condition. Looking from the gate of M1 and M2, when it looks, it is trying to see only the downward path. Okay, there is no connection from the gate to the drain, as you all know. So from the perspective of this, when I look down, I see the same node Vs, and from this M2 gate, when I see, I could able to see the same thing. Okay, so as far as this VID is concerned, the circuit seems to be the same. Either you stand from here or stand from here, it looks the same, it looks alike, which means that the circuit is symmetric. Okay, provided the W by L of 1 and W by L of 2 are same. Okay, so under that condition, the circuit is symmetric from the perspective of my V in or VID. Okay, so due to which I can bring this node to the value of 0. Whenever the circuit is symmetric, the very first statement is that when I apply an antisymmetrical inputs, then this common node would be brought down to 0. Clear? So now let us deal with what value of VGS1 I have to take and what value of VGS2 I have to take. Now what is the value of VGS1 that I have here? So it would be plus VID by 2, because it's an antisymmetrical inputs, right? So if I have plus here, what about the potential across this VGS? It would be minus VID by 2, and this VID equally splits. If at all, if I have a different W by L factor here and a different W by L factor here, then I cannot split this VID into two halves. Okay, that is completely a different story. But as far as this circuit is concerned, I am going to assume my M1 W by L factor and M2 W by L factor are same, and due to which the VID will be equally splitted. It's an antisymmetrical inputs, due to which I have plus here and a minus here. Okay. Now, what is the current that flows through this drain of M1? Okay, so it will be equal to ID1, small ID1, and that value is GM1 times that of VID by 2. Now what about the current flow through this M2 then? Yeah, so I can write the current as ID2 that is equal to minus GM2 VID by 2, or if I flip the current flow, then I can just write this one as just plus GM2 VID by 2. Okay, I've just removed the negative sign and I flipped it. Is that as clear? Yeah. So now we know that this structure, what is the structure of this M3 and M4? They are current mirrors. So any current flow here will also be reflected at this particular point, right? Now this current is equal to ID, yeah, that is equal to GM1 VID by 2. Now there is also one more current that is coming towards this node, which is GM2 VID by 2. And what is the current, total current that flows out of this I out? Yeah, it is ID1 plus ID2, and the currents would be like GM1 VID by 2, and the other end I have GM2 VID by 2. But if I assume that GM1 is equal to GM2, then I can write it as GM1 comma 2 into VID. Okay, I have just added both the halves. and assuming that the value of gm1 is exactly equal to gm2, then I can just have a single term which is gm1 comma 2. Clear? Now, what is my capital Gm out of the circuit? You see, from the previous case we had only half the value of gm1 comma 2, and right now when I remodified this load, then I could able to get the complete value of gm, okay, and none of the current flow through this particular path is being wasted. Clear? Now, let us do the computation for R out. What are the things that we need to take care? Okay, first of all we have to remove the VID, so both the gates would be grounded. Now apply Vx. Yeah. So this is the end result, right? Now, is the circuit symmetric? No. Where is my input for this? The input is my Vx, right? Now I want to measure this Ix. Now with respect to the input, the circuit is not symmetric. The reason is that this node is not same as that of this node. What did I say when we discussed about this large signal analysis of common mode? Whatever the value of Vf has to be adapted to my Vout, okay? But whatever Vout I have, yeah, so this statement is not always true. So whatever the Vf that I have has to be adapted by Vout, but Vout cannot define the value of Vf. Clear? Is that making sense? Because I am changing only my drain. The change in the drain will not affect my VGS of this transistor. So I cannot impose this constraint from one end to the other end. Okay. Is that clear? So a Vout cannot define my Vf, but Vf can define my Vout. Okay? Yeah. So now, is the circuit symmetric right now? No, because I have a Vout that is equal to Vx right now, but this node need not to be equal to Vx. Okay? So this node is completely at a different potential. Because of that, the circuit is not symmetric from the perspective of my Vx. And whenever the circuit is not symmetric, what happens to the node Vp? Cannot be equal to 0, right? So due to which I have this kind of structure. Now, how would we evaluate the R out for the circuit? Yeah, so whenever I try to draw the small signal model, what happens to this ISS? It's open circuit, so I don't need to consider any of these things. Okay? Now the whole point is that when we had this structure, right? Yeah. So you can able to get back to the same structure. What is the impedance that I see through this drain of M2? 2 times that of R0 2. So we know from this point to this point, from the drain of M2 to the drain of M1, I have a resistance, and that value of resistance is equal to 2 times R0 2. So I'm going to use that relation. Okay? So the equivalent resistance that I see from this point to this point is equal to this quantity. Now, how is that possible? Yeah, but the whole point is that whatever the current that flows into the drain of M2 has to come out of this. Only from that perspective I'm telling, okay? And after this, either it goes directly to the ground or goes through a resistance, doesn't matter. Am I right? So you see, if I have a resistor, this is 2R2, okay? Whatever the current that flows will come here. Whether this node is directly connected to the ground or connected through a resistance doesn't matter for me. This resistance is always equal to twice the value of R02 is what I'm arguing, okay? Yeah, so I'm just going to apply that condition, and then that condition would give us, so what is the impedance of this, small signal impedance of this M3? Okay, so I have a resistance whose value is 1 by GM3 in parallel with RO3, and from here to here there is a resistance whose value is twice RO1 comma 2, and then I have, I'm just going to visualize this Ix as a branch of 3 currents, okay? Now one of the current is through this path, okay, path number 1. Because of this current mirroring structure, the same current would then be reflected here as well, right? On this particular node. Are you clear? Okay. So this current flow would then be reflected here through the value of VGS. Okay. So that is my second current. there is also one more current. What is that current? Yeah, so even the drain has a small signal resistance, right? And what is that small signal resistance when I look through the drain of M4? RO4. Now what is the current that flows through this device? It would be Vx divided by RO4 will give us the third current. So we basically have this Ix as a summation of three currents. Okay, one is this particular path current, the second one is the mirror of the same path 1 current, and the third one is the current flow through this RO4. Okay, so I'll stop here. I want you to compute this and come up with the answer. So we'll discuss about the answer in the 3:45 class. Clear? Yeah, so for this differential input, we want to calculate the differential gain of the circuit. So we had this mechanism of computing the GM first, followed by this, we had the mechanism of computing our R out next. Okay, so the discussion about this GM was already done in the class. So we'll just look at the final expression of it. So what was the final expression that I got out of the circuit? Yeah, it would be like GM 1, 2. So when I compared this particular output with the previous structure that we had, this has almost all the GMs of my input device, okay? Whereas the previous circuit, we had only half of the circuit just because we are not utilizing the other branch GM, okay? But just because I added this mirror structure, I could able to utilize that M1 GM onto my output, okay? Yeah. So now we'll just quickly catch up this R out expression. So in the case of R out, what was the very first step that I have to do? Yeah, so first of all, I need to short those inputs to the ground. So we went on doing that. Okay, and then we also apply some potential Vx, and I want to measure this Ix. Okay, now in this case, the statement that I stated here is that right now the V out is completely defined by a potential Vx. Okay, so this is what is defining my V out potential right now, and as I said, the V out cannot define my Vf. Okay, so the potential that I have across my Vf is completely different from the potential that I have across V out. That is, V out is currently having a value of Vx, but it is not that the Vf is having the same value of Vx. Clear? Yeah. So now based on this, we try to analyze the entire circuit. Now, the current Ix could be split into three current components. Okay. So one is the current that flows through this M1 all the way to the ground. Okay. So let me take it as I1, and the other current is the mirroring current. So whatever the current that flows in this particular path through this M3 and M4 mirror combination, I would end up having appearing here, right? So, okay. So this I2 is nothing but my I1 itself, just because of the mirroring. Okay. But apart from these two currents, there is also one more third component of my current Ix. What was that? Yeah, M4. Just because there is a finite amount of resistance whose value is RO4, I have a potential of Vx at this particular node. Okay. So whenever there is a potential difference between any resistance, obviously there will be a current flow through them, right? So here there is a current flow which I label it as I3. Clear? Now, the very first thing is that the computation of I3 is pretty simple. Okay, so what is the value of this I3? Yeah, it is just Vx by RO4. Okay, so that is done. But what about the computation of I1? Because I1 is the one that we have to think around. So once I get the value of I1, then the value of I2 is just the mirror of I1 itself. So I can just use the value of I1 for I2 as well. Okay. So what we did in order to compute the value of I1. Yeah, so we went on with the discussion that stating that whatever the resistance that I have between the drain of this M2 to the drain of my M1, it is considered as an equivalent resistance whose value is just twice the value of RO1, 2. Now that is the equivalent resistance that I have between this node to this node. Okay. After this, what I have is again one more impedance whose value is defined as 1 by GM3 in parallel with RO3. Okay. So now that I just want to compute the value of the I1. So what would be your answer for this? So there is a potential difference right from this point towards this point. Okay. There is a current flow through this, and that current is nothing but my I1. So if you want, I will just redraw the structure. I have a resistance from this point to this point, and the value of that resistance is just this quantity. And from this point to this point, there is one more resistance, and that value is nothing but 1 by GM3 in parallel with RO3. Okay. Now, at the end of this particular path, this is connected to my VDD. So when I translate to my small signal model, that goes to an AC ground, due to which I put a ground here. Okay. Now at this particular point, what I have is just the value of Vx, and I am trying to measure I1. Okay. So what is the value of I1 then? Yeah, Vx by the summation of these two impedances. It's as simple as that. Okay. So now that I can get the value of I1 to be equal to Vx divided by all of the impedances that are in series, I just add them up. Okay. So now that I've got the value of I1, and this I1 is actually flowing through this mirroring structure, due to which it gets copied even here. Okay. So the current is flowing through this mirror structure, something in an upward direction, and the similar upward direction would end up having across this M4 as well. Okay. That is nothing but my I2. Clear? So the value of I1 and the value of I2 would be equal just because of the mirror combination of M3 and M4. Okay. So just because of this mirror, it would be same. So due to which I just want to completely write my expression of this Ix. Okay. So the total value of Ix is nothing but twice, because I1 and I2 are same, so I just add both of them with a factor of 2 with this quantity, which is Vx divided by 2 times that of Rho1, 2 plus 1 by Gm3 in parallel with Rho3. And then there is also one more component of it, right? So what was that current component that I have? Yeah, it is Vx by Rho4. Okay. Now, I'm just going to perform some simplification to this particular formula. So the very first thing is that I'm going to assume that the value of this 1 by Gm3 is small. Okay. So if this guy is small, then obviously the combination of this, could be reduced down to 1 by Gm3. Now, as I said, this 1 by Gm3 is small. So when I add something with a very large quantity like twice the value of Rho1, 2, then one could approximate even this to be equal to twice the value of Rho1, 2. So what I have at the denominator of the first term is just twice the value of Rho1, 2. That's it. Okay. So now I have a factor of 2 here sitting here, and then one more factor of 2 at the bottom. Okay. And then I have the value of Ix, and here again the value of Vx. Okay. So I can cancel out the common terms here, which is 2 and 2, and the value of Rx, if I see, it is Vx by Ix. What is this combination of 1 upon 1 by Rho1? Yeah, it's a parallel combination of Rho1, 2 in parallel with Rho4. That's it. Okay. Yeah. Actually, at the end of the class, there was a discussion. I don't know whether the person is. Yeah. So he had asked me about how I can visualize that particular impedance. So his argument was something like this. So this was his argument, like, because whenever I look through this drain of this structure, we know that any impedance that I have at this particular point would be magnified. So if that is the case, there is something flaw or something that it was disturbing him. So then I also thought about it, just because, as he said, the argument is true. Just because in this case, I'm just adding this twice the value of Rho1 plus 2, and then I'm neglecting the entire quantity here, right? So what has really happened here is that if you see here, the impedance that I have here is basically something different. Okay, so let us first try to evaluate what is the impedance value that I have here. What would be that value here? But I'm looking into the source. Okay, yeah. So I'm just looking into the source, and I'm looking at a resistance value. Yeah. So yeah, let us take it as RD, this particular term. So the RD would be diminished by the intrinsic gain of this quantity. Okay, and due to which the impact of this particular resistance appearing onto my node at this particular point is very minimum. Okay, so that's the reason why we can also think that the resistance that I have from here to here is equal to twice the value of Rho1, 2, which means that, are you getting it? Okay, because in the previous case, so what was the resistance that I had from this drain to this drain? To Rho1, where the drain of my M1 is at the ground. Okay, whereas in the case where I have drawn here, the drain of this M1 is not at the ground. Okay, but there is a kind of added resistance along with it. But this resistance doesn't make much voltage drop across it, just because the resistance when I look here, it becomes smaller, further smaller. The 1 by GM3 is already small, and when I look through this M1 source terminal, it becomes further diminishes. Okay, so which means that the drop across this small impedance would be much more minimum. Okay, so I could able to visualize that this node is almost closer to the value of ground itself. Okay, does it make sense? Okay, so even if you are not getting it, it's fine. So the whole point is that the resistance from the drain of M2 to the drain of M1 is twice the value of R01, 2.